For billions of years, something ancient has been racing toward us through the darkness between stars, something that existed before Earth formed, before the sun ignited, before life found its first foothold on our world. Now, in December 2025, it arrives. 3I Atlas, the third interstellar visitor ever detected by human civilization. And on December 19th, it makes its closest approach to our planet. You've heard the rumours circulating online, claims about magnetic disruptions that could cripple our technology, theories about its true nature that challenge everything astronomers thought they knew. Speculation about what it might do when it reaches us, whispered across social media platforms and conspiracy forums alike. But here's what makes this genuinely unprecedented. This object has travelled through hostile radiation, extreme cold, and unimaginable distances for potentially 8 billion years. It survived what should have destroyed it 1,000 times over. It endured conditions that would vaporize steel, freeze helium solid, and tear apart mountains. And now, travelling at speeds that defy comprehension, faster than anything humanity has ever built, it's aimed directly at our solar system's heart. What happens when an object this ancient, this fast, this mysterious reaches Earth? The question isn't whether 3I Atlas will affect our planet. The question is how. Because everything about this visitor contradicts what we know about comets. Its composition is wrong. Its trajectory is statistically impossible. Its behaviour defies the natural laws we've observed for centuries. Even its timing seems almost calculated, arriving at a moment when humanity finally has the tools to witness it. Harvard astrophysicist Avi Loeb has identified 10 distinct anomalies. 10 ways this object shouldn't exist, according to our current understanding of physics and astronomy. Other scientists have detected unusual activity emanating from its position for the first time in observational history. Some observations suggest non-gravitational acceleration, meaning something is pushing it beyond the sun's gravity alone. Something we can't fully explain. Is 3I Atlas just a comet from another star system? Or have we been watching something else entirely approach Earth for months? Something that doesn't fit comfortably into our categories and classifications? Stay with me. In the next several minutes, we're going to investigate exactly what 3I Atlas will do to Earth, separating verified science from viral speculation, examining the evidence that has astronomers worldwide monitoring this object around the clock, and revealing what December 19th really means for our planet and everyone on it. We're going to look at the data NASA doesn't headline, the measurements that puzzle even veteran astronomers, the questions that remain unanswered despite months of observation. Because while the official statements sound reassuring, the scientific papers tell a more complex story, a story of an object that shouldn't be here, behaving in ways it shouldn't behave, arriving at Earth's doorstep after a journey so long that it began when the universe itself was barely half its current age. Before we uncover what's actually approaching us, I need you to understand something crucial. What you're about to learn changes the conversation entirely, and it starts with understanding what this visitor truly is and where it came from. Before we dive deeper into what makes 3I/ATLAS so extraordinary, if you're watching because you're curious about what's really heading toward Earth, make sure you hit that subscribe button right now. That way, you won't miss the discoveries we're about to reveal in the next few minutes, the science that explains everything about this ancient cosmic visitor. Now, let's look at what astronomers have discovered about 3I/ATLAS's trajectory, because the path it's taking tells a story that's even more puzzling than its origins. Let's establish what we know with certainty before we dive into what puzzles even the experts. 3I Atlas is what astronomers call an interstellar object, a visitor from beyond our solar system, from the vast spaces between stars where darkness stretches for light years in every direction. The 3I designation means it's only the third such object humanity has ever detected and confirmed. Think about that for a moment. 3. In all of human history, with all our telescopes and satellites and detection systems, we've confirmed just 3 visitors from interstellar space. The first was Oumuamua in 2017, that cigar-shaped mystery that sparked years of debate and speculation. The second was Borisov in 2019, which behaved more like what we expected from a comet. And now 3I Atlas, arriving with characteristics that somehow managed to be both familiar and deeply strange. When we say interstellar, we're not just talking about something from far away. We're talking about an object that originated in a completely different stellar system, orbiting a different star, formed from a different protoplanetary disk billions of years ago. This thing doesn't belong to our Sun. It wasn't born here. It's a cosmic refugee, expelled from its home system through gravitational interactions we can only imagine, then sent wandering through the galactic void for an incomprehensible span of time. Current estimates suggest 3. The Atlas has been travelling through space for potentially 8 billion years. To put that in perspective, 8 billion years ago, Earth was barely a billion years old. Life on our planet consisted of single-celled organisms. The continents hadn't formed their current shapes. Oxygen was still accumulating in our atmosphere, and this object was already travelling, already moving through the frozen darkness between stars, already on a journey that would eventually bring it to our solar system. What kept it intact across such distances and durations? Interstellar space isn't empty. It's filled with radiation, cosmic rays, dust particles travelling at relativistic speeds. Any object exposed to these conditions for billions of years should be fundamentally altered, its surface eroded, its composition changed by continuous bombardment. Yet 3i Atlas arrived here still cohesive, still active, still capable of producing the gas and dust we associate with comets. The speed alone marks it as alien to our system. 3i Atlas is moving relative to the Sun at velocities that dwarf anything gravitationally bound to our star. It's travelling on what astronomers call a hyperbolic trajectory, a path that means it will never return. It's not captured by our Sun's gravity. It's not going to settle into an elliptical orbit like the comets we're familiar with. It's passing through, a cosmic visitor that will arrive, swing past the Sun, and then continue back into interstellar space, never to return. This trajectory tells us something profound. 3. I-Atlas has more than enough velocity to escape the Sun's gravitational influence. It's not slowing down to stay. It's not being captured. It came from somewhere else, and it's going somewhere else, and we just happen to be here during its brief passage through our neighbourhood. But here's where the story gets interesting. Most objects entering our solar system from interstellar space would arrive from random directions, reflecting the chaotic nature of galactic motion. Stars orbit the galactic centre at different speeds, in different planes, creating a three-dimensional soup of trajectories. You'd expect interstellar visitors to come from above or below the plane of our solar system, from odd angles that reflect their alien origins. 3. I-Atlas doesn't do that. Its trajectory aligns remarkably well with the ecliptic plane, the flat disk where Earth and the other planets orbit. It's moving through our solar system almost as if it belongs here, almost as if it knows the way, following the same general plane that defines our cosmic neighbourhood. This alignment is one of the first things that caught astronomers' attention, one of the first hints that something about this visitor doesn't match expectations. The object itself appears to be several kilometres across based on its brightness and activity level. That makes it substantial, not a tiny pebble but a mountain-sized chunk of ancient ice and rock, and whatever else comprises the building blocks of planets in other stellar systems. It's massive enough to hold together under its own gravity, massive enough to have survived its billions of years' journey without disintegrating into smaller fragments. And now this massive, ancient, impossibly fast visitor is in our solar system, moving along a path that will bring it relatively close to Earth by cosmic standards. NASA and ESA have been tracking it continuously since detection, calculating and recalculating its trajectory, measuring its speed and composition, trying to understand what exactly we're dealing with. Because while the basics are clear, it's an interstellar comet passing through our system. The details reveal layers of complexity that challenge our assumptions about what comets should be and how they should behave. Every telescope that can be pointed at 3i Atlas has been pointed at it. Hubble has observed it. The James Webb Space Telescope has observed it. Ground-based observatories across the world have dedicated precious observation time to studying this visitor. Spacecraft like ESA's JUICE probe, currently on its way to Jupiter, has been tasked with observing 3i Atlas as it passes. The scientific community recognises that opportunities like this are vanishingly rare. We might not see another interstellar visitor with this much advance notice in our lifetimes. So what have all these observations revealed? That's where the straightforward story of an interstellar comet passing through begins to develop complications. That's where the questions start to outnumber the answers, and the path forward becomes a journey into understanding what this visitor truly represents, and what it means for Earth as December 19th approaches, let me tell you about a number that's been quietly circulating among astronomers, a number that doesn't make headlines, but that tells you everything about why 3I Atlas is so extraordinary. The probability of an interstellar object entering our solar system and aligning with the ecliptic plane the way 3I Atlas does is approximately 0.2%, 0.2%, less than 1 in 500. Those aren't impossible odds, but they're the kind of odds that make scientists pause. When you're dealing with the vastness of space and the randomness of galactic dynamics, finding an interstellar visitor that moves through our solar system, almost as if it's following the roadmap of planetary orbits, raises eyebrows. It's like watching a stranger walk into your home and navigate directly to the kitchen without asking for directions. Technically possible, but odd enough to notice the trajectory of 3I Atlas tells a story written in mathematics and gravitational physics. It entered our solar system from the direction of the constellation Ursa Major, moving on a path that brought it first toward the outer reaches of our planetary system. As it fell inward toward the Sun, accelerating under the immense gravitational pull of our star, it passed relatively close to Mars, then Venus, executing a cosmic dance that brought it within striking distance of multiple planets. Now, before anyone panics, striking distance in astronomical terms means millions of kilometers. 3I Atlas never posed an impact threat to any planet in our system. The trajectory was clear from early calculations that this visitor would pass safely by every world in our solar system, including Earth. But the proximity is still remarkable. Most interstellar objects would sail through the outer solar system and leave without ever coming close to the inner planets. 3I Atlas is diving deep, penetrating into the heart of our system, passing through the orbits of terrestrial worlds. On October 30th, 2025, 3I Atlas made its closest approach to the Sun, what astronomers call perihelion. This is the moment when a comet experiences maximum heating, when solar radiation bombards its surface with intensity, when ice vaporizes into space and creates the spectacular tails we associate with these objects. The perihelion passage was a crucial moment for observations because it revealed how 3I Atlas would respond to our Sun's heat. Heat from a star it had never encountered before, heat from a stellar environment completely foreign to whatever distant system gave it birth. What happened at perihelion raised more questions than it answered, but we'll get to that shortly. For now, understand that 3I Atlas survived its close solar approach. It didn't disintegrate, it didn't break apart under the thermal stress. It rounded the Sun and began its outbound journey, and that's the phase it's in now, moving away from our star, back toward the outer solar system and eventually back into interstellar space. But on its way out on December the 19th, 2025, it makes its closest approach to Earth. The numbers are precise, approximately 270 million kilometers. That's about 1.8 astronomical units, where 1 astronomical unit is the distance from Earth to the Sun. To put that in perspective that doesn't require a physics degree, it's roughly 1.8 times the distance between our planet and our star. The Moon is about 380,000 kilometers away. 3I Atlas will be more than 700 times farther than the Moon. This is not a close approach in the sense that should cause anyone alarm. There is zero, and I mean zero, chance of impact. The trajectory has been calculated and confirmed by multiple space agencies. 3I Atlas will pass at a safe distance, nowhere near close enough to pose any physical threat to our planet, but it will be close enough for detailed observation, close enough for amateur astronomers with decent telescopes to potentially spot it, close enough that this is the best opportunity humanity will ever have to study this particular visitor, because once it passes Earth, it continues outbound, fading into the distance, eventually becoming too faint to observe as it returns to the interstellar medium. After Earth, 3. I Atlas continues its journey outward, and here's where things get even more interesting. In March 2026, just a few months after its Earth approach, 3. I Atlas will pass relatively close to Jupiter, and ESA's JUICE spacecraft, which launched to study Jupiter and its moons, will be in a position to observe this encounter. There's even discussion in the scientific community about whether JUICE could be maneuvered to get closer to 3I Atlas, to perform a flyby that would give us unprecedented close-up data on an interstellar object. Think about what that would mean. We've never conducted a close flyby of an interstellar visitor. Oumuamua was detected only as it was already leaving our solar system. We spotted it too late to send anything to intercept it. Borisov was observed from Earth, but again, too far and too fast for any spacecraft rendezvous. 3i Atlas represents a genuine opportunity to get close, to measure, to analyse with instruments designed to study cometary composition and activity. But back to that trajectory, because there's another element that deserves attention: the path. 3i Atlas follows isn't just aligned with the ecliptic, it's also moving in a direction that brings it through the planetary orbits at angles and times that maximise its exposure to our worlds. It's almost as if, and I'm being very careful with language here because I don't want to suggest anything not supported by evidence, it's almost as if the trajectory was designed for observation, designed to bring this object close enough to multiple planets to be noticed, to be studied, to make an impression. Now, the scientific consensus is clear. This trajectory is the result of gravitational dynamics, of the same physics that governs every object in the universe. When 3i Atlas was ejected from its home system billions of years ago, it was set on a course determined by velocity, direction, and the gravitational influences it encountered along the way. The fact that this course brought it through our solar system in such a memorable way is coincidence. Extremely unlikely coincidence, but coincidence nonetheless. Yet there's a reason scientists are watching so intently. There's a reason every major observatory has dedicated time to this object. Because when coincidences pile up, when the unlikely becomes the observed, scientists pay attention. Not because they're jumping to exotic conclusions, but because rare events often teach us things common events never could. 3i Atlas, with its improbable trajectory and its close approaches to multiple planets, is teaching us about galactic dynamics, about the frequency and nature of interstellar visitors, about what exists in the space between stars, and it's raising questions. Questions about whether we're properly understanding the distribution of matter in our galaxy. Questions about whether interstellar objects are more common than we realized, and we're only now developing the technology to detect them regularly. Questions about what other visitors might be passing through our solar system unnoticed, too faint or too fast for our current detection capabilities. As December 19th approaches, the trajectory brings 3i Atlas to the point where it will be most visible, most accessible to study, most present in our immediate cosmic neighbourhood. And that's when we'll have our best chance to answer the question that's been building throughout this investigation. What exactly is this thing, and why does it behave so strangely? Now we arrive at the heart of the mystery, the elements that transform 3i Atlas from an interesting astronomical event into a genuine scientific puzzle. Because while the trajectory is unusual, it's the composition and behaviour of this object that have sparked debates among astronomers and captured the attention of researchers who normally deal in certainties and calculations, not speculation and mystery. Let's start with what comets are supposed to be. When we think of comets, we think of dirty snowballs, mixtures of ice and rock, primarily water ice with various other frozen compounds mixed in comets from our own solar system. The ones that formed alongside our planets from the same primordial disk of gas and dust follow predictable patterns. They're rich in water. When they approach the sun and heat up, that water ice vaporizes into space, creating the distinctive tails that have fascinated humans for millennia. We know their composition. We've studied them extensively. We've even landed spacecraft on comets to analyse their makeup directly. 3i Atlas doesn't follow the pattern. The spectroscopic observations, measurements of the light reflected and emitted by the comet, reveal something unexpected. 3i Atlas is dominated by carbon dioxide and carbon monoxide, not water. Now, comets do contain these compounds, but usually as minor components, secondary to the water ice that makes up their primary volatile material. 3i Atlas flips that script. It's CO2-rich and water-poor, showing a composition that's rare even among the thousands of comets we've observed from our own solar system. Why does this matter? Because composition tells us about formation conditions. The ratio of different ices, the presence or absence of certain molecules, reveals the temperature and pressure conditions where a comet formed. Water-rich comets form in regions where water ice is stable. CO2-dominated comets suggest formation in colder regions, farther from their parent star, in environments where even water ice might not be the dominant frozen compound. 3i Atlas's composition suggests it formed in the outer reaches of its home stellar system, in regions so cold and distant that carbon dioxide dominated over water. That's not impossible. Such regions exist in planetary systems, but it's unusual, and it raises questions about what kind of stellar system would produce a comet with these characteristics, what kind of protoplanetary disk would favour CO2 over H2O in its frozen materials. But the composition is just the beginning of the anomalies. There's also the matter of polarization. When light reflects off a comet's surface and dust particles, it becomes polarized. The light waves align in particular directions. By measuring this polarization, astronomers can learn about the size, shape, and composition of the dust particles surrounding the comet. It's a standard technique, used routinely to characterize cometary dust. 3i Atlas shows extreme negative polarization values that are unprecedented in cometary observations. The measurements indicate dust particles with properties unlike any comet dust we've previously encountered. Some researchers have suggested this could indicate the presence of unusual materials in the comet's composition, materials that don't match the standard mix of silicates and organic compounds we find in solar system comets. One specific element has caught attention: nickel. Spectroscopic observations have detected nickel in 3i Atlas's coma, the cloud of gas and dust surrounding the nucleus. Nickel isn't uncommon in comets, but the abundance detected in 3i Atlas is higher than typically observed. Some scientists have pointed to this as evidence of unusual formation conditions or composition. Others have suggested it might indicate the object has experienced more processing, more alteration by cosmic rays during its billions of years in interstellar space, which brings us to perhaps the most contentious anomaly: non-gravitational acceleration. When astronomers track the precise position of comets over time, they can detect tiny deviations from purely gravitational trajectories. These deviations are caused by outgassing. When ice vaporizes, it creates jets of gas that act like tiny rocket engines, pushing the comet slightly off its predicted path. This effect is well understood and commonly observed in comets. 3i Atlas shows evidence of such acceleration, but the pattern doesn't quite match expectations. Some observations suggest the acceleration is stronger than the observed outgassing would produce, or directed in ways that don't align with the visible jets and plumes. This has led to intense debate in the astronomical community. Is this just a normal cometary process that appears odd because we're observing an interstellar visitor with different formation history? Or is something else contributing to the acceleration? This is where Avi Loeb enters the conversation. Loeb, a Harvard astrophysicist known for his willingness to consider unconventional explanations, has argued that 3i Atlas shows characteristics that deserve serious consideration beyond standard cometary models. He's identified multiple features: the trajectory alignment, the composition, the acceleration patterns, that individually might be explicable, but collectively paint a picture he finds difficult to reconcile with natural comet behavior Loeb has suggested. And I want to be clear that this remains highly controversial and rejected by most of the astronomical community, that some interstellar objects might warrant investigation as potential artifacts, rather than purely natural phenomena he's not claiming. 3i Atlas is definitely artificial, but he's arguing that the anomalies are significant enough to justify more intensive study and a willingness to consider all possibilities. The mainstream scientific community pushes back hard against these suggestions. Most astronomers studying 3i Atlas see an unusual comet, certainly, but still a comet, a natural object formed by natural processes, displaying characteristics that are rare but not impossible. They argue that our sample size of interstellar objects is so small that we simply don't know what normal looks like for comets from other stellar systems. Maybe CO2-dominated composition is common elsewhere in the galaxy. Maybe the polarization values reflect formation conditions we don't have in our own solar system. Maybe the acceleration patterns are within the range of natural cometary behavior, just at the extreme end. There's also the rapid brightening to consider. As 3i Atlas approached the Sun, it brightened significantly faster than models predicted. This sudden increase in activity suggests either a composition that's more volatile than expected, or a surface that was heavily covered with insulating material that suddenly broke away, exposing fresh ice to solar radiation. Comets sometimes do this. They can have crusts of non-volatile material that build up over time, then crack off, causing sudden outbursts of activity. But again, the timing and intensity of 3i Atlas's brightening didn't quite match standard models. It was too much, too fast. in ways that required adjusting assumptions about the comet's composition and structure. Then there are the colour changes. Observations showed that the colour of the light reflected from 3, the atlas changed as it approached perihelion, not dramatically, but measurably. Colour changes in comets can indicate changing composition of the material being released, or changing particle sizes in the dust coma. For 3I Atlas, the changes suggested evolving activity, possibly different layers of the comet being exposed and vaporized as it got closer to the Sun. And finally, there's the anti-tail. Some comets develop what's called an anti-tail, a tail that appears to point toward the Sun rather than away from it. This is an optical illusion caused by viewing geometry in the distribution of large dust particles that lag behind the comet in its orbit. 3I Atlas has shown evidence of anti-tail formation, which in itself isn't anomalous. Many comets do this. But combined with everything else, it adds to the sense that this object is displaying the full range of complex cometary behaviours, all compressed into one visitor. What do we make of all these anomalies? The scientific process demands we start with the simplest explanations, and only move to more exotic hypotheses when the simple ones fail. The simple explanation is that 3I Atlas is a comet formed under conditions different from those in our solar system, travelled through interstellar space for billions of years under bombardment from cosmic rays and radiation, and arrived here displaying characteristics shaped by that unique history. Every anomaly can be explained through some combination of unusual but natural formation conditions, radiation processing during its journey, and observational limitations on our part. But the fact remains that researchers are watching closely, analysing every data point, because rare events expand our understanding. Whether 3I Atlas is ultimately classified as an extremely unusual natural comet, or remains a mystery with some unsolved aspects, it's teaching us about the universe beyond our solar system. It's showing us what exists in the space between stars. It's forcing us to question assumptions we built from studying only the comets of our own stellar neighbourhood. And as December 19th approaches, as this anomalous visitor makes its closest pass to Earth, the question shifts from what is it to what will it do? December 19th, 2025, mark it on your calendar, not because you need to prepare for anything, but because it represents a moment of cosmic significance that happens perhaps once in a human lifetime. On this day, 3I Atlas reaches its closest point to Earth, and for a brief window of time we share our local space with a visitor that has travelled longer and farther than anything else humanity has ever observed up close. Let's establish the facts with precision, because precision matters when addressing fears and speculation. On December 19th, 3I Atlas will pass Earth at a distance of approximately 270 million kilometres. That's about 1.8 astronomical units, roughly 1.8 times the distance from Earth to the Sun. At this distance, the gravitational influence of 3I Atlas on Earth is negligible, and I don't mean negligible in the sense of very small but technically present. I mean negligible in the sense that you exert more gravitational influence on your neighbour, standing next to you, than 3I Atlas will exert on our entire planet. Gravity falls off with the square of distance, double the distance, and the gravitational force becomes 1/4 as strong. 3I Atlas will be nearly 2 astronomical units away, and it's a comet nucleus, a few kilometres across, made of ice and rock, with a mass that's minuscule compared to Earth. The Moon, which orbits just 380,000 kilometres away and is massive by comparison, exerts gravitational forces on Earth that we experience as tides, the rising and falling of ocean water, the subtle flexing of Earth's crust. 3I Atlas will pass more than 700 times farther away than the Moon. With a fraction of the Moon's mass, do the mathematics, and the gravitational effect rounds to 0. There will be no tidal disruptions, no earthquakes triggered by gravitational stress, no orbital perturbations. Earth will continue its stately orbit around the Sun completely unaffected by the gravitational presence of 3I Atlas. Anyone telling you otherwise is either misunderstanding the physics or deliberately spreading misinformation. What about magnetic effects? This one circulates online, claims that 3I Atlas could disrupt Earth's magnetic field, cause auroras, interfere with satellites or power grids. Let's address this clearly. Earth's magnetic field is generated by the motion of liquid iron in our planet's outer core. This dynamo effect creates a magnetic field that extends tens of thousands of kilometres into space, protecting us from solar radiation and cosmic rays. It's a planetary-scale phenomenon driven by internal heat and rotation. 3I Atlas has no magnetic field of its own. Comets don't generate magnetic fields, they're not metallic. They don't have internal dynamos, they're chunks of ice and rock. They can interact with the sun's magnetic field, which is carried through the solar system by the solar wind, but they don't produce their own magnetic environments. And even if 3I Atlas somehow possessed a magnetic field, at a distance of 270 million kilometers, it would be far too weak to affect Earth. Our own Sun, with its immense magnetic field, is 150 million kilometers away, and we're bathed in its magnetic influence constantly. The idea that a small comet nearly twice as far away could disrupt Earth's magnetic field has no basis in physics. But what about the ion tail? Comets produce two types of tails, a dust tail made of tiny solid particles, and an ion tail made of charged gas molecules. The ion tail is shaped by the solar wind and always points away from the sun. It's made of material that's been electrically charged by solar radiation, and it streams behind the comet like a banner, sometimes stretching for millions of kilometers. Could Earth pass through 3I Atlas's ion tail on December 19th? The geometry says no. Remember, 3I Atlas is moving outbound from the sun when it makes its closest approach to Earth. Its tails, both dust and ion, point away from the sun, away from the inner solar system. Earth won't cross through these tails because we're not positioned in their path. We're off to the side, watching the comet pass at a safe distance, with its tail streaming in a different direction entirely. But let's say hypothetically that Earth did pass through a cometary tail. What would happen? We have historical data on this because it's happened before. In 1910, Earth passed through the tail of Halley's Comet. There was public panic at the time, fears of poisonous gases, of atmospheric contamination, of catastrophic effects. What actually happened? Nothing. Absolutely nothing. Cometary tails are incredibly diffuse. The gas and dust are spread so thinly across such vast distances that passing through a tail is like walking through a room where someone lit a match an hour ago. You might detect a few molecules, but there's no substance there, no density, nothing that could affect a planet's atmosphere. Earth is protected by an atmosphere that's thick and robust, constantly bombarded by material from space, micrometeorites, dust particles, solar wind, and that handles all of it without any noticeable effect on the surface. A cometary tail, even if we pass through one, would contribute fewer particles than a typical meteor shower, and we experience those regularly without concern. So gravitationally, magnetically, and in terms of physical material, 3I Atlas poses no threat to Earth during its December approach. What the closest approach does offer is an observational opportunity for astronomers. December 19th and the surrounding weeks represent the best viewing window for 3I Atlas. The comet will be visible in Earth's night sky for observers with telescopes, appearing as a faint fuzzy object moving slowly against the background stars. It won't be naked eye visible for most people. It's not going to be the kind of spectacular comet that dominates the sky, like Hale-Bopp in 1997 or Neowise in 2020. But for those with the equipment and knowledge, it will be there, a visitor from another stellar system close enough to study in detail. Professional observatories will be making the most of this opportunity. Spectroscopic measurements to analyze composition, photometric observations to track brightness changes and rotation, polarimetric studies to understand the dust properties. Every telescope that can be brought to bear will be recording data, because opportunities to study interstellar objects up close are vanishingly rare. There's also the possibility, though not confirmed, that space agencies might release special observations from spacecraft. Hubble might capture images James Webb could potentially observe in infrared, detecting the thermal emission from the comet's nucleus. JUICE, en route to Jupiter, will certainly be observing as the comet passes through its vicinity. All of this data will contribute to our understanding of what exists beyond our solar system. For those wondering if they can see it, the answer depends on your equipment and location. 3. I-Atlas will require at least a moderate amateur telescope, perhaps 15 to 20 centimeters of aperture, and dark skies away from city lights. Astronomy clubs and public observatories might host viewing events. It won't be dramatic. It will be a small, faint patch of light, unremarkable to the untrained eye. But knowing what it is, knowing that you're looking at matter from another star's planetary system, material that has travelled for billions of years to pass through our neighbourhood, That gives the observation weight and significance far beyond its visual appearance. December 19th also represents a moment for reflection on how far we've come. A century ago, we didn't know galaxies beyond our Milky Way existed 50 years ago. We didn't know if planets orbited other stars. Now we're tracking and studying objects from those other stellar systems as they pass through our own. We're analysing their composition, measuring their trajectories, learning from their presence. That progression is extraordinary, and 3i Atlas is part of that story. So what actually happens on December 19th? From Earth's perspective, not much. Life continues normally. The comet passes by at a safe distance, too far to exert any influence, too faint for most people to notice. But for those paying attention, for those who understand what they're witnessing, it's a moment of connection to the larger cosmos. It's a reminder that we're part of a galaxy filled with stellar systems, many of which produce comets and asteroids and debris that sometimes wanders into neighbouring territories. And it's a setup for what comes next. The scientific analysis, the measurements, the conclusions drawn from months of observations. Which brings us to the core question. What will 3i Atlas actually do to Earth? Now we arrive at the answer you've been waiting for, the resolution to the question posed at the beginning. What will 3i Atlas do to Earth? And I'm going to give you that answer directly, without equivocation or hedging, because you deserve clarity after following this investigation through all its complexities and mysteries. 3i Atlas will do nothing to Earth. Nothing at all. No gravitational disruption, no magnetic interference, no atmospheric effects, no seismic activity, no electromagnetic pulses, no technology failures. Earth will continue spinning on its axis, orbiting the Sun, supporting billions of human lives and countless other species, completely unaffected by the passage of this interstellar visitor. But let me explain why that's the answer, and why it's still the right answer, even given all the anomalies and unusual characteristics we've discussed. Because understanding why something doesn't happen is often as important as understanding what does happen. The reason 3i Atlas will have no effect on Earth is fundamentally about scale and distance. Physics doesn't care about mystery or speculation. It cares about mass, distance, velocity, and the forces that govern interactions between objects. 3i Atlas is a comet nucleus several kilometers across. Earth is a planet with a diameter over 10,000 kilometers and a mass that exceeds the comets by a factor of billions. The distance between them at closest approach is vast. Hundreds of millions of kilometers of empty space. For 3i Atlas to affect Earth gravitationally, it would need either tremendous mass or extreme proximity. It has neither. Even the Moon, which is relatively close and relatively massive, only produces tides, gentle risings and fallings of water, and minor flexing of rock. 3i Atlas is smaller, farther and weaker in every measurable way. The gravitational force it exerts on Earth at closest approach is less than the gravitational force exerted by the device you're watching. This on magnetic effects require a magnetic field, and comets don't generate magnetic fields. They can carry some residual magnetism in metallic grains embedded in their structure, but this is negligible. They interact with the Sun's magnetic field carried by solar wind, but they don't produce fields of their own. And even if 3i Atlas somehow possessed a planetary-scale magnetic field, which it absolutely doesn't, the distance is too great for any effect on Earth. Our planet's magnetosphere extends about 10 Earth radii into space on the sunward side, and stretches into a long tail on the night side. 3i Atlas passes more than 10,000 Earth radii away. No interaction is possible. What about debris? Could material from 3i Atlas rain down on Earth, entering our atmosphere? The geometry says no. The comet's orbit doesn't intersect Earth's orbit. We're not crossing through its path. The material shed by the comet, the dust and gas that create its coma and tails, moves along trajectories determined by solar radiation pressure and the solar wind. This material spreads out behind the comet, forming the characteristic tails that point away from the Sun. Earth's position during the December approach places us outside the path of this material. We're not downwind, so to speak. We're off to the side, watching from a distance. Even if we were positioned to encounter some debris from 3i Atlas, the effect would be minimal. Cometary debris entering Earth's atmosphere creates meteor showers, beautiful displays of light as tiny particles burn up miles above the surface. We experience these regularly from various comets whose orbits do intersect Earth's orbit. The Perseids every August come from Comet Swift-Tuttle. The Leonids in November come from Comet Tempel-Tuttle. These showers are harmless and predictable. The particles are so small and so diffuse that they pose no threat to anything on the ground, or even to satellites in orbit. But we're not going to encounter debris from 3I Atlas during this pass because, again, the geometry doesn't support it. So if all the physical effects are negligible or non-existent, where do the online claims come from? Why are people suggesting that 3I Atlas could disrupt GPS systems, cause power grid failures, trigger earthquakes, or produce other catastrophic effects? The answer, unfortunately, is a combination of misunderstanding, misrepresentation, and deliberate fear-mongering. Let's address the most common claims directly. Claim 3. I-Atlas will disrupt Earth's magnetic field. Reality: it has no magnetic field strong enough to interact with Earth's magnetosphere at this distance. This claim likely stems from confusion about how comets interact with solar wind, or a fundamental misunderstanding of magnetic field strength and distance relationships. Claim: the comet's tail contains toxic gases that could poison Earth's atmosphere. Reality: cometary tails are so diffuse that they contain fewer particles per cubic kilometre than the best laboratory vacuums. Even if Earth passed through a tail, which we're not, the amount of material entering our atmosphere would be infinitesimal. Earth's atmosphere is protected by constant influx of material from space, and cometary tails represent a tiny fraction of what we encounter daily from solar wind and interplanetary dust. Claim: gravitational interaction with 3I Atlas could trigger earthquakes or volcanic eruptions. Reality: the gravitational force is far too weak. We're talking about a force millions of times weaker than the tidal forces the Moon exerts on Earth every day. If Earth's geology doesn't respond to lunar tides in catastrophic ways, it certainly won't respond to 3I Atlas passing more than 700 times farther away. Claim: the comet's electrical charge or electromagnetic properties could interfere with satellites, power grids, or communication systems. Reality: comets don't generate electromagnetic pulses or carry electrical charges sufficient to affect technology at planetary distances. The ion tail is electrically charged, but it's also incredibly diffuse and shaped by solar wind, not by any internal power source. At hundreds of millions of kilometers distance, any electromagnetic effects are unmeasurable. Where these claims gain traction is through selective citation of real science, taken out of context or misapplied. For example, yes, comets can have ion tails that are electrically charged. Yes, comets can contain carbon monoxide, which is toxic to humans. Yes, passing close to massive objects can have gravitational effects. But the devil is in the details, the distances, the concentrations, the magnitudes. When you actually calculate the numbers, when you apply the physics correctly, the scary scenarios evaporate. There's also a pattern we see repeatedly in online discourse around astronomical events: the tendency to assume unusual equals threatening. 3I Atlas is unusual, we've established that thoroughly. It has characteristics that puzzle astronomers and behaviours that don't perfectly match standard models, but unusual doesn't mean dangerous. The universe is vast and varied, producing objects and phenomena across a spectrum of possibilities. Finding something at the rare end of that spectrum is interesting scientifically, but it doesn't automatically imply threat. The scientific community has been clear and consistent. 3I Atlas poses no danger to Earth. NASA, ESA, and every credible astronomical institution monitoring this object agrees. The trajectory has been calculated with precision. The mass and composition have been measured. The distance at closest approach is known, and all of these factors combine to produce a conclusion of zero threat. So what will 3I Atlas do to Earth? It will give us data. It will teach us about interstellar space and the diversity of objects that travel through it. It will provide observations that will fuel scientific papers and expand our understanding of comets formed in other stellar systems. It will offer amateur astronomers a chance to observe something genuinely rare and special. It will spark conversations about our place in the galaxy and the frequency of interstellar visitors. But it won't disrupt, damage, or threaten our planet in any measurable way. Physics is clear on this, and physics doesn't negotiate. The real story of 3I Atlas isn't about danger, it's about discovery. It's about what we're learning from this visitor's composition, trajectory and behaviour. It's about how this one object is expanding our understanding of the galaxy beyond our solar system. And that brings us to the legacy, what 3I Atlas means for science, and why its passage through our neighbourhood matters for more than just the December approach date. remove the speculation and conspiracy theories, strip away the fearful predictions, and what remains is something far more valuable than any disaster scenario could ever be: genuine scientific discovery. 3i Atlas represents a rare opportunity to study material that formed in another stellar system, material that has been processed by billions of years of exposure to interstellar conditions, material that carries information about places we may never be able to visit directly. That's the real significance of this visitor. Think about what we're actually observing here. When you look at 3i Atlas through a telescope, the photons hitting your eye left that comet's surface a certain amount of time ago based on its distance, roughly 15 to 20 minutes at closest approach. But the matter comprising that comet, the actual atoms and molecules, formed billions of years ago in a protoplanetary disk around a completely different star. This is matter that never belonged to our Sun, never participated in the formation of our planets, never had any connection to our stellar neighbourhood until now. What can that matter teach us? Quite a lot, actually. The composition of 3i Atlas tells us about the conditions in its home system. The carbon dioxide dominance suggests formation in the cold outer regions of a protoplanetary disk, perhaps around a star cooler than our Sun, or in a system where the architecture placed material like this farther from the central star than our solar system's equivalent regions. The presence of certain molecules and the ratios between different compounds act as chemical fingerprints, revealing temperature, pressure, and chemical environment during formation. But beyond formation conditions, 3i Atlas carries another story written into its structure, the story of interstellar travel. For billions of years, this object has been exposed to galactic cosmic rays, high-energy particles that travel through the galaxy and bombard any material they encounter. These cosmic rays gradually alter the chemical and physical properties of surfaces, breaking molecular bonds, creating new compounds, changing colours and reflective properties. By studying 3i Atlas, scientists are learning about these cosmic ray effects. How does organic material weather under billions of years of radiation exposure? How deep does the processing penetrate? What kind of surface layers build up? These aren't academic questions. They're crucial for understanding the interstellar medium, for predicting what future interstellar visitors might look like, and for planning missions to study such objects. The Hubble Space Telescope has observed 3i Atlas multiple times. Capturing detailed images and spectra, Hubble's capabilities allow measurements of composition, size, and activity level with precision that ground-based telescopes can't always match. Each observation adds data points to our understanding. James Webb, with its infrared capabilities, can see thermal emission from the comet, the actual heat radiating from its surface and interior. This tells us about how efficiently the comet absorbs and re-radiates solar energy, which in turn tells us about its surface properties and composition. ESS JUICE spacecraft, currently on its multi-year journey to Jupiter, has been tasked with observing 3i Atlas during its outbound journey. JUICE carries instruments designed to study icy moons and cometary material, and those instruments can be turned toward this interstellar visitor to gather data that ground-based observations can't provide. There's been serious discussion in the scientific community about whether JUICE could perform a distant flyby, not a close intercept, which would require too much fuel, but a trajectory adjustment that would bring the spacecraft closer to 3i Atlas for better observations. And here's where things get really exciting from a scientific perspective: the March 2026 encounter with Jupiter. After passing Earth in December 2025, 3i Atlas continues outbound and will pass relatively close to Jupiter in March 2026. This encounter offers a unique opportunity because Jupiter's immense gravitational field will slightly alter 3i Atlas's trajectory, not dramatically, but measurably. By comparing the predicted path with the actual post-Jupiter path, scientists can refine their measurements of the comet's mass and potentially detect effects from outgassing or other non-gravitational forces. Jupiter also produces intense radiation belts, regions of space around the planet filled with high-energy particles trapped by its magnetic field. 3i Atlas will pass through these radiation belts, experiencing a brief but intense bombardment that might trigger additional outgassing or surface changes. Observing how the comet responds to this sudden radiation dose could reveal information about its subsurface structure and composition. JUICE will be in position to observe this Jupiter encounter, potentially giving us before and after comparisons of 3I Atlas's activity level and appearance. If the comet shows changes attributable to the radiation environment, it would provide unprecedented data on how cometary material responds to radiation, data that would be valuable for understanding both solar system and interstellar comets. Beyond the observations of this specific object, 3I Atlas is contributing to a larger understanding of interstellar object populations. Before 2017, we had never detected an interstellar visitor. Now, we've confirmed 3, Oumuamua, Borisov, and 3I Atlas, in just 8 years. That's a remarkable detection rate given that our survey capabilities are still relatively limited. Statistical models suggest that several interstellar objects pass through the inner solar system every year, most of them too small or too faint to detect with current telescopes. The Vera Rubin Observatory, currently under construction in Chile, will begin operations soon with capabilities far exceeding current survey telescopes. Rubin is expected to detect interstellar visitors regularly, perhaps dozens per year, transforming these rare curiosities into routine observations. What will we learn when interstellar objects become routine? We'll learn about the frequency of planetary system formation across the galaxy. We'll learn about the efficiency of planet formation processes, how much material gets ejected versus how much gets incorporated into planets. We'll learn about the diversity of stellar systems, because different types of stars produce different types of protoplanetary disks, which produce different types of comets and asteroids. We'll also learn about galactic dynamics. The trajectories of interstellar objects tell us about stellar motions, about the distribution of matter in our galactic neighborhood, about gravitational interactions that occur over millions of years as stars move through the galaxy. Each interstellar visitor is a probe, carrying information from its home system and its journey, information encoded in trajectory and composition. 3I Atlas is teaching us that interstellar comets can be compositionally diverse. Borisov looked quite similar to solar system comets, suggesting that comet formation produces similar outcomes across different stellar systems. 3I Atlas, with its unusual composition and characteristics, shows us that diversity exists, that not all comets from other stars will resemble our local comets, that diversity is valuable data for planetary formation theories. The scientific papers emerging from 3I Atlas observations will be published over the coming years as researchers analyze the data thoroughly. These papers will contribute to fields ranging from planetary science to galactic astronomy, from organic chemistry to radiation physics. The value of a single object can ripple outward through multiple disciplines when that object is rare and information-rich. And there's a human element to this legacy as well, the inspiration factor. Every major astronomical event, every close comet pass, every unusual discovery brings new people into astronomy. Students choose to study astrophysics because they were captivated by a comet they saw or read about. Amateur astronomers buy their first telescope to observe an event like this. Public interest in space science increases when there's something tangible to focus on, something happening in real time that people can follow. 3I Atlas, despite or perhaps because of all the speculation and mystery surrounding it, has captured public attention in ways that purely academic discoveries often don't. People are talking about interstellar objects. They're learning about trajectories and composition and the difference between comets and asteroids. They're engaging with science, asking questions, seeking understanding. That engagement is valuable beyond any single data point or measurement. So when we ask why 3I Atlas matters, the answer is layered. It matters scientifically because it provides rare data about interstellar space and object diversity. It matters historically because it's only the third such object ever detected, making it part of the beginning of a new era in astronomy. It matters educationally because it teaches us about processes and environments we can't easily study otherwise. And it matters culturally because it connects humanity to the larger cosmos, reminding us that we're part of a galaxy full of other stellar systems, some of which are sending their material our way. The legacy of 3I Atlas will ultimately be measured not in the sensational claims or the December approach date, but in the scientific understanding it generates and the curiosity it inspires. Step back from 3I Atlas for a moment and consider what its existence represents in a larger context. We now know with certainty that interstellar objects regularly pass through our solar system. The question is no longer do they exist, but rather how common are they and what does that tell us about the galaxy? Statistical models based on the detection rate of interstellar objects suggest something remarkable. Approximately 7 interstellar visitors pass within 1 astronomical unit of the Sun every year. 7 objects per year from other stellar systems, travelling through our immediate cosmic neighbourhood, most of them completely undetected because they're too small or too faint for our current survey capabilities. Think about what that means. Right now, as you're hearing these words, there are likely interstellar objects somewhere in our solar system, travelling through the space between planets, on trajectories that will carry them back out into the galaxy. We don't see them because they're too dim, or because they're not in the right position, or because our telescopes are pointed elsewhere. But they're there, silent visitors passing through, carrying matter from distant stellar systems. This realization changes how we think about our solar system. We've historically conceptualized our solar system as a closed system. The Sun and its family of planets, moons, asteroids, and comets, all gravitationally bound together, all sharing a common origin in the same protoplanetary disk. That picture is correct for the vast majority of objects we observe. But it's not complete. Our solar system is also a thoroughfare, a region of space that interstellar objects traverse on their galactic wanderings. The galaxy is full of stellar systems, each producing its own population of comets and asteroids through planet formation processes. Gravitational interactions within those systems, close encounters between planets, gravitational assists from massive bodies, scattering events during formation, eject some percentage of this material into interstellar space. That ejected material doesn't just disappear, it continues moving through the galaxy, following trajectories determined by its velocity and the gravitational influences it encounters. Over millions and billions of years, these ejected objects spread through galactic space. Some remain relatively close to their home systems. Others, like 3I Atlas, travel for billions of years, crossing vast distances, potentially encountering stellar systems far from where they originated. And when their trajectories happen to intersect with another stellar system, like ours, they become interstellar visitors, passing through as strangers, here for a cosmic moment, and then gone. Our detection of these objects is improving rapidly. Oumuamua was detected only as it was leaving. We spotted it too late to get ideal observations. Borisov was detected further out, giving us more time to study it. 3I Atlas was detected early enough that we've been able to track it through its entire passage, from approach to perihelion to departure. This progression shows our improving capabilities. The next major leap comes with the Vera-Rubin Observatory. Rubin is designed to survey the entire visible sky repeatedly, searching for anything that changes or moves. Its large mirror and advanced camera will detect objects far fainter than current surveys can find. When Rubin comes online, the detection rate for interstellar objects is expected to increase dramatically, from the current rate of perhaps 1 per few years to potentially dozens per year. What will we learn when interstellar visitors become routine detections rather than rare events? We'll start to see patterns in their compositions, their sizes, their trajectories. We'll be able to categorize them, to understand which types are common and which are rare. We'll learn about the efficiency of planet formation across different types of stellar systems. Stars more massive than the Sun, stars less massive, stars with different metallicity, stars at different galactic locations. We'll also learn about planetary system architecture. The distribution of interstellar object trajectories tells us about the typical distances at which objects are ejected, which in turn tells us about where planets commonly form and what gravitational dynamics characterize typical systems. It's indirect evidence, but it's evidence we couldn't get any other way without visiting other stellar systems directly. There's also a planetary defense aspect to understanding interstellar visitors. While 3I Atlas poses no threat to Earth, and while the vast majority of interstellar objects will pass safely by, we need to understand the population to assess any potential future risks. If interstellar objects regularly pass through our solar system, there's some non-zero probability that eventually one might be on a trajectory that intersects Earth's orbit at the wrong time. The probability is extremely low. Space is vast and Earth is small, but it's not zero. Planetary defense efforts currently focus on solar system objects, asteroids and comets that orbit the Sun, and whose trajectories we can predict years or decades in advance. Interstellar objects are different because they arrive from outside our system, often with little warning. Oumuamua gave us only weeks from detection to departure. Future similar objects might give us more or less time depending on their trajectories and when we detect them. Building a catalogue of interstellar visitor characteristics, their typical sizes, compositions, velocities, helps planetary defense planning. It allows us to model potential scenarios, to understand what kind of warning times we might have, to develop response capabilities for different types of encounters. It's not about panic or fear. It's about responsible preparation, about understanding the environment Earth exists within. But beyond defense considerations, the bigger picture is about understanding our place in the galaxy. We're learning that our solar system is not isolated. It's part of a galactic ecosystem where matter moves between stellar systems, where the products of planet formation in one star's neighbourhood eventually travel to another star's neighbourhood. We're all connected through these wandering objects, through this exchange of material across light years and eons. 3, Atlas has travelled for billions of years to pass through our system. In another few million years, it will encounter another stellar system, perhaps one where life exists, perhaps one where intelligent beings will observe it and wonder about its origin just as we wonder about it now. The material that comprises 3I Atlas might someday fall into another star, or collide with another planet, or be captured into another system's Oort cloud. Its journey doesn't end when it leaves our solar system. It continues, potentially for billions more years, carrying matter across the galaxy in an eternal wandering. And we're part of this process too. Some of the comets and asteroids in our solar system will eventually be ejected through gravitational interactions. They'll become interstellar objects themselves, carrying matter from our sun's protoplanetary disk to other stellar systems. Billions of years from now, astronomers orbiting other stars might detect these former solar system objects and study them the way we're studying 3I Atlas now. The exchange flows in both directions. This realization that we're embedded in a galaxy-wide system of material exchange, that we're connected to other stellar systems through these wandering messengers, shifts perspective. It makes our solar system feel less like an isolated island and more like a node in a vast network, a location in space that's visited by travellers from distant origins, a place that also sends out its own travellers to distant destinations. 3I Atlas is one such traveller, and its passage through our neighbourhood is a reminder of these connections. It's a visitor from a place we'll likely never visit ourselves, bringing information about conditions and processes in a stellar system potentially thousands of light years away, and we have the privilege through our technology and scientific knowledge to observe it, to study it, to learn from it. The bigger picture is that Earth exists in a dynamic galactic environment, where such encounters will become increasingly common as our detection capabilities improve. We're entering an era where interstellar visitors will be part of regular astronomical observations, where students will study these objects in classes, where data from dozens or hundreds of interstellar comets and asteroids will inform our understanding of galactic structure and stellar system diversity. 3I Atlas is part of that transition, part of the shift from rare curiosity to routine observation, and its legacy will include not just what we learn from this specific object, but how it contributes to establishing the field of interstellar object studies as a standard part of astronomy. We've followed the evidence through trajectory analysis, composition measurements, anomaly investigations, and threat assessments. We've examined what 3I Atlas is, where it came from, what makes it unusual, and what it will do during its December approach to Earth. Now comes the moment of synthesis, the point where we integrate all the information and arrive at a conclusion about what we're actually observing. The scientific consensus is clear and consistent. 3. Atlas is a natural comet, formed billions of years ago in another stellar system, ejected into interstellar space through gravitational dynamics, and now passing through our solar system on a trajectory that will carry it back into the galactic medium. Every major space agency, every institutional observatory, every peer-reviewed analysis has reached this same conclusion. The anomalies that sparked speculation and controversy can be explained through a combination of unusual formation conditions, billions of years of cosmic ray processing and observational limitations. Does that mean 3I Atlas is ordinary? Absolutely not. Within the category of natural comets, 3I Atlas represents something extraordinary, a visitor from another stellar system, displaying characteristics shaped by an environment and history completely different from solar system comets. Its carbon dioxide-rich composition reflects formation conditions we don't have in our system. Its extreme polarization values result from surface processing by interstellar radiation over geological timescales. Its trajectory alignment is statistically unlikely but not impossible. Its non-gravitational acceleration is consistent with cometary outgassing, just at the unusual end of the observed range. Each anomaly, examined individually and in context, falls within the bounds of natural phenomena. Unusual natural phenomena, certainly, but natural nonetheless. The universe is vast and varied, producing objects across a spectrum of possibilities. Finding something at the rare end of that spectrum doesn't require exotic explanations. It requires recognition that rare and unusual are not synonyms for impossible or artificial. Avi Loeb's controversial suggestions about potential artificial origins for some interstellar objects have value in one specific sense. They remind us to question assumptions, to examine evidence carefully, to consider possibilities before dismissing them. Science advances through skepticism and investigation, not through uncritical acceptance of conventional wisdom. Loeb's willingness to propose unconventional hypotheses serves that purpose. But the evidence for 3I Atlas doesn't support artificial origin hypotheses. Every measurement, every observation, every data point is consistent with natural cometary processes. The composition makes sense for a comet formed in cold outer regions of a protoplanetary disk. The outgassing behavior matches expectations for comets with high CO2 content. The trajectory, while unusual in its ecliptic alignment, is dynamically possible and doesn't show signs of deliberate maneuvering or control. The brightening and color changes are consistent with cometary activity responding to solar heating. What 3I Atlas represents, then, is not mystery in the sense of unexplainable phenomena, but mystery in the sense of imperfect knowledge. We don't know exactly which stellar system it came from. That information is lost to billions of years of galactic motion. We don't know all the details of its formation environment. We can infer but not confirm we don't know its internal structure. Our observations are limited to the surface and the material it releases, but not knowing everything doesn't mean we know nothing. The scientific method allows us to build understanding from incomplete information, to draw conclusions bounded by evidence, to separate what we can confidently state from what remains uncertain. The verdict on 3I Atlas is that it's a natural wonder, an object that teaches us about the diversity of cometary bodies, about the processes that shape matter in interstellar space, about the frequency and characteristics of visitors from beyond our solar system. It's a probe from another part of the galaxy, carrying information encoded in composition and behavior, information we're only beginning to decode. And what of December 19th? That date represents an observational milestone, not a threat or catastrophe. On that day, 3I Atlas will pass closest to Earth, offering our best opportunity to study this visitor before it fades back into the depths of space. For astronomers, it's a data collection opportunity. For amateur observers, it's a chance to witness something genuinely rare. For everyone else, it's a reminder that we live in a dynamic universe where such encounters occur, where our solar system is visited by material from distant origins, where the cosmos is more interconnected than we once imagined. The real story of 3I Atlas isn't about danger or conspiracy or hidden threats. It's about discovery and understanding. It's about humanity's growing capability to detect and study objects that previous generations would never have known existed. It's about what we learn when we observe carefully, measure precisely, and think critically about evidence. A century from now, when interstellar objects are detected routinely and their characteristics are well catalogued, 3I Atlas will be remembered as one of the early examples, one of the visitors that helped establish our understanding of this population. It will be cited in papers about interstellar object composition, about cosmic ray processing effects, about the frequency of visitors from other stellar systems. Its anomalies will be understood in context, as natural variations in a diverse population rather than as unsolved mysteries. But for now, in this moment, 3I Atlas occupies a special position. It's one of only 3 confirmed interstellar objects ever detected by humanity. It's passing through our solar system during our lifetimes, during the era when we first gained the ability to observe such visitors in detail. That makes it part of our story, part of the astronomical narrative of the early 21st century. When December 19th arrives, look up if you can. You won't see much, a faint fuzzy spot in a telescope, unremarkable to the untrained eye, but know that you're looking at matter from another star's planetary system, material that has travelled across unimaginable distances and durations, a visitor that connects our solar system to the larger galaxy. That's worth observing. That's worth understanding. That's worth remembering. 3i Atlas will do nothing to Earth, but it will do something for us. It will expand our knowledge, challenge our assumptions, and remind us that the universe is full of wonders waiting to be discovered, natural wonders, explained through physics and chemistry and astronomy, but wonders nonetheless. And that, ultimately, is the answer to what 3i Atlas will do. It will teach us if we're willing to learn. The visitor from another star is passing through, and we have the privilege of witnessing it. That privilege comes with responsibility, to observe accurately, to reason carefully, to separate fact from speculation, and to appreciate the genuine marvels of the cosmos without needing to manufacture false threats or imagine non-existent dangers. 3i Atlas is remarkable enough on its own terms. It doesn't need embellishment. It just needs to be understood for what it is. A natural messenger from the deep reaches of space, here briefly and then gone, leaving us with knowledge and perspective we didn't have before. That's the verdict. That's the answer. And that's the truth about what 3i Atlas will do to Earth.